Good morning. Last week we talked about taking a golf ball and dropping it from rest and describing the motion it had. We decided that the only force acting on the ball was the force of gravity. When taking a look at this image, we saw per unit time the change of position of the golf ball got bigger and bigger. So we know from that the ball was speeding up. Over the weekend, you created a data table, and yesterday you built a position versus time graph for that ball. Now, what I'm showing you is not a position versus time graph for that ball, but a position versus time graph that you saw earlier this year. Earlier this year, we took a look at some fake wheel and axle data, and we plotted the points on a position versus time graph and noticed that the dots did not line up. In fact, we found out the best fit for this set of data was a curve. The first way we tried to linearize the data was to build a velocity versus time graph using slopes of tangent lines. We drew tangent lines that touched along the outside of the curve. Notice the green line. It just barely touches the curve at the 1 second mark. The slope of that tangent line tells us the velocity at 1 second. Notice the orange line runs alongside the curve, just barely touching it at the 2 second mark. The slope of that line gives us the velocity at 2 seconds. Likewise, the tangent line drawn at 3 seconds gives us the slope. The tangent line drawn at approximately 3 seconds would give us the velocity of the wheel and axle at 3 seconds. From that, we built a time and velocity data table. For each clock reading, we put in the corresponding velocity. And from that, we built a velocity versus time graph. Using the clock readings, original clock readings, and their corresponding velocities that came from the slopes of the tangent lines, we could see as time increased, the velocity increased at a constant rate. It was speeding up. When we did a further analysis of the graph, we found out the slope was approximately 11.3 centimeters per second, which meant for every second, the velocity of the wheel and axle was increasing. We called that new idea of velocity changing or increasing acceleration. Here is a specific mathematical model for this velocity versus time graph and a general equation for this velocity versus time graph. But that wasn't the only way we found out the wheel and axle was accelerating. Next up, we took a more general idea. We took the idea that if we took a line and connected it from 0 to 6 seconds, the slope of that black line there would give us the average velocity from 0 seconds to 6 seconds. So the average velocity of this wheel and axle over the whole time was equal to the tangent line from 0 to 6 seconds. Well, we also drew a line from 2 to 4 seconds. When doing that, we found out that that slope was also parallel and therefore the same steepness as the line we drew from 0 to 6 seconds. Finally, we drew a tangent line at 3 seconds. Notice the steepness of each of these three lines are all approximately the same. In doing so, we found out that the average velocity for a time interval equals the instantaneous velocity at the time in the middle of that time interval. So in this case, since the wheel and axle was speeding up from 0 to 6 seconds, the average velocity from 0 to 6 seconds happens to be the exact velocity at the 3 second mark, because 3 seconds is the time that fits in between, or is right in the middle of 0 to 6 seconds. Using that idea, we built this crazy chart, which had change in time, change in position, time midpoint, and average velocity. When filling these out, we came up with formulas for each one of them. And this basically came out to the idea that if you could find how much the time changed from 0 to 1 second, and how much the position changed during that 1 second, and found the time value that fit in the middle of that time interval, you would find the instantaneous velocity at that time in the middle. We filled that out with the corresponding values. From 0 to 1 second was 1 second, from 0 to 5 centimeters was 5 centimeters, the time that fell in the middle of 0 and 1 second was 0.5 seconds, and then the average velocity, which is change in position divided by change in time, so the change in position was 5, divided by our change in time was 1. 5 divided by 1 is 5, and that's centimeters per second. We then use these values to build a second velocity versus time graph. We called this velocity versus time midpoint. Now remember, time midpoints are not any different than other clock readings. It's just how we went about finding these velocities. Once we found the slope of this line, again, this units came out to be centimeters per second per second. So we say here that for every 1 second, the velocity increased by 10 centimeters per second. Again, you've got a specific mathematical model and a general equation that we could use for a mathematical analysis. But there was a third way. The third way we found out about calculating or linearizing this information, we found out from other mathematicians. They had found previously, if you had a top open curve like that, that sometimes when you square whatever's on the x-axis, it'll linearize the data. So since this is a position versus time graph, if we made a position versus time squared graph, it would then linearize that data. So that was our next job. We had clock readings and positions and time squared values, and we filled out our time squared values, and we plotted a position versus time squared graph. Now remember, even though these are squared clock readings, we have to make sure that they take up the same amount of space per second squared down below. Remember, these are time squared, so they are seconds squared. When we took a closer look at this slope, we got a slope of 5 centimeters per second squared, or 5 centimeters per second per second. So coming up with a specific mathematical model, as we've done for all year long, the y-axis, or if you take a look at your y equals mx plus b, we knew the name of the y-axis was position, the name of the x-axis was time squared, but we put the slope of 5 centimeters per second squared in there. We compared the slope of this graph to the slopes of the other graphs we got from making the velocity versus time graphs. Here's one of the earlier graphs we looked at. The slope of the velocity versus time graph was 10 centimeters per second squared, and we already know that's the acceleration for this wheel and axle. Well, using the exact same data, when we built a position versus time squared graph, we only got a slope of 5 centimeters per second squared, which is half of the other slope. Since the other slope was the acceleration, 5 is half of 10, so that means the slope of a position versus time squared graph is 1/2 the acceleration. So, in summary, when we took a look at a uniformly accelerating object, when we looked at a position versus time graph that had a top open curve, we could take the slopes of tangent lines or look at velocity at time midpoints and build a velocity versus time graph. In our velocity versus time graphs, we came up with a directly proportional relationship. We found that the slope of our velocity versus time graphs were at the rate of acceleration. The rate at which velocity changed with respect to time is the acceleration, right? But the slope of the position versus time squared graph was also directly proportional, but it was half as steep as the other one, which told us the slope of a position versus time squared graph was 1/2 the acceleration. What you're charged with is you need to pick one of these 3 ways to linearize your information. You can build a velocity versus time graph from tangent lines, a velocity versus time midpoint graph, or a position versus time squared graph. If you'd like to know the easiest way to do it, squaring your clock readings and building a position versus time squared graph, most people find most time efficient. Whichever kind of linearized graph you build, you do need to make a mathematical analysis, which would include a y equals mx plus b, a specific mathematical model, or a general equation. Or for the velocity versus time graph, you'd want to look at your specific mathematical model or general equation. Now, I know I went through this stuff pretty quickly, but we've already been through this stuff earlier in the school year. These are all from Unit 2, Worksheet 1, from first semester, which you have in your notes, or you could slow this video down and take a look at the individual parts. There will also be a PDF of this document attached. I hope that helps.